Right now, about 350 million kilometers from Earth, something is moving toward the Sun that breaks the rules of physics. Its tail points the wrong way. It's ejecting nickel without iron, which shouldn't be chemically possible. And a Harvard scientist just calculated there's only a 0.2% chance this trajectory happened naturally. In 6 days, we'll know if it's a comet or something else entirely. This is 3I Atlas, the third interstellar visitor ever detected, and it's doing things that make scientists question everything they thought they knew about comets. Let me show you why this object has the scientific community completely captivated. The tail that defies gravity. When the Twin Telescope in the Canary Islands captured images, in August, astronomers noticed something impossible. A stream of gas and dust, about 3.7 miles long, pointing directly at the Sun. Not away from it, toward it. Every comet we've ever observed has its tail blown away from the Sun by solar radiation and solar wind. That's basic physics. But 3I Atlas is spewing material in the opposite direction. They're calling it an anti-tail. Professor Avi Loeb from Harvard is one of the few scientists publicly addressing this anomaly. Most comet experts are ignoring this detail, he says, insisting the object has a standard origin. But Loeb argues that this tail orientation doesn't match any known mechanism of comet degassing. Loeb points to the combination of factors: the anti-tail, the nickel without iron, the improbable trajectory, the age and speed of the object, the way it navigated past Venus, Jupiter, and Mars while remaining largely undetected from Earth. Individually, these anomalies are puzzling. Together, they form a pattern. And Loeb argues that pattern is more consistent with technology than with natural processes, NASA's official position, and what it means. Despite all of this, NASA classifies 3I Atlas as a natural comet. They've seen the same data. They've reviewed the spectroscopy, the trajectory, the chemical composition, and their conclusion is that this is an interstellar comet, extraordinary but natural. The question is, are they right, or are they defaulting to the standard explanation because the alternative is too disruptive? Historically, scientific institutions resist paradigm shifts. They demand overwhelming evidence before accepting revolutionary ideas. That's not necessarily wrong. It's how science maintains rigor. But it also means that genuinely anomalous objects might get categorized as normal, simply because the system isn't ready to acknowledge the alternative. The European Space Agency's JUICE probe will be monitoring 3I Atlas in November and December. Ground-based observatories will continue tracking it. If this is a comet, the thermal stress from the Sun will likely cause it to fragment. The icy nucleus will vaporize, the structure will break apart, and we'll see a typical cometary death. That's what happens to comets when they get this close to the Sun. But if it doesn't fragment, if it remains intact, then Loeb's alternative scenarios, including technological origins, become much harder to dismiss. October 29th is the key date. That's when we'll see if the object behaves like a comet or like something else. The pattern that can't be ignored. Let's step back and look at the full picture. 3I Atlas has an anti-tail pointing toward the Sun instead of away from it. It's ejecting nickel without iron, violating chemical principles. It's on a trajectory with a 0.2% natural probability. It's older than our solar system. It's moving faster than typical comets. It has an unusual cylindrical shape and green glow. It navigated through the solar system avoiding detection. And it's arriving at the Sun at a time that would be ideal for a gravitational assist maneuver. Any one of these facts is interesting. 2 or 3 together are intriguing. But all of them in one object? That's a pattern. And patterns demand explanations. Either nature is pulling off a series of statistically improbable coincidences, or we're looking at something that doesn't fit the natural model. This is why scientists are so captivated. This is why Loeb is willing to stake his reputation on the possibility of artificial origins. Because the data, taken as a whole, doesn't align with what we know about comets. What happens next? The next few weeks are critical. As 3i Atlas makes its closest approach to the Sun, every available instrument will be watching. If it fragments, the debate ends. It's a comet, albeit a very unusual one. The anomalies will be explained away as rare but natural occurrences. But if it survives intact, if it continues on its trajectory without breaking apart, then the conversation changes completely. Then we have to seriously ask, what is this thing? Where did it come from? And why is it here? For now, 3i Atlas remains the most compelling interstellar object ever detected. It's challenging our understanding of comets, chemistry, and celestial mechanics. It's forcing scientists to confront possibilities they'd rather not consider. And it's doing all of this while slipping past our most powerful instruments, almost as if it knows exactly when and where we're looking. Whether it's a comet or something else, 3i Atlas is already rewriting what we thought we knew. In a few days, we'll have answers. Or we'll have even bigger questions. The water that shouldn't be there. Let's talk about one of the most baffling aspects that scientists are still struggling to explain. When the Swift telescope turned its instruments toward 3i Atlas in October, it detected something that made physicists pause. Water vapor. Lots of it. Approximately 40 kilograms every single second, pouring off this object in a steady stream. To put that in perspective, imagine 40 1-liter bottles of water evaporating into space every second. That's 2,400 liters per minute, 144,000 liters per hour. It's an enormous outgassing rate. But here's the problem. 3i Atlas is currently at about 3 astronomical units from the Sun. That's roughly 450 million kilometers away, about the distance of the asteroid belt, far beyond Mars. At that distance, the Sun's energy is only about 11% as strong as it is at Earth's orbit. It's barely enough to warm ice, let alone vaporize it at such a massive rate. Normal comets don't start producing significant water until they're inside 2 AU, and they really activate inside 1.5 AU. But 3i Atlas is blasting out water from a distance where it should still be frozen solid. The thermal energy reaching it simply isn't sufficient to explain this level of activity. So what's powering it? Some scientists suggest there might be subsurface heat, perhaps from radioactive decay of elements inside the nucleus. But that raises more questions. What kind of composition would generate enough internal heat to drive this much outgassing after billions of years? Radioactive elements decay over time. After 7 to 10 billion years, most of the short-lived isotopes would be long gone. You'd need something with a very long half-life, and even then, the heat output would be minimal. It doesn't add up. Another theory is that the object contains highly volatile materials, substances that vaporize at extremely low temperatures. Maybe exotic ices we don't commonly see in solar system comets. But spectroscopic analysis hasn't revealed anything unusual enough to account for this. The composition is strange, yes, with that extreme CO2 to water ratio, but nothing screams exotic volatiles that could justify 40 kilon per second at 3 AU. The physics just doesn't close, and that's deeply unsettling to scientists who've spent careers modeling comet behavior. The industrial compound that appeared out of nowhere. Here's another detail that barely made headlines, but deserves attention. In the spectroscopic data, researchers detected nickel tetracarbonyl. That's NiCO4, a compound where a nickel atom is bonded to 4 carbon monoxide molecules. Now, nickel tetracarbonyl is not some common cosmic molecule. On Earth, it's an industrial chemical used in refining processes and metallurgy. It's toxic, volatile, and forms under very specific conditions. Finding it in a comet is bizarre. Finding it in an interstellar object ejecting nickel without iron is even stranger. Nickel tetracarbonyl forms when nickel reacts with carbon monoxide under particular temperature and pressure conditions. In industrial settings, we create it deliberately. But in space, the natural formation pathway is unclear. You'd need metallic nickel, you'd need carbon monoxide, and you'd need the right environment for them to combine. This suggests that somewhere in 3I Atlas, there's metallic nickel, not just nickel bound in silicate minerals or other compounds. Metallic nickel, reacting with CO-rich gases, forming this industrial chemical. It's as if there's a refinery process happening inside this object. Or something that mimics one. Could this be a clue to the missing iron? If there's a mechanism that's isolating and concentrating nickel, perhaps forming compounds like nickel tetracarbonyl, could that explain why we're not seeing iron? Maybe the iron is there, but it's locked away in a different phase, a different mineral structure, while the nickel is being preferentially mobilized and ejected. That's highly speculative, but it's one of the few ways to reconcile the chemistry with the observations. The alternative, that this object genuinely lacks iron, remains chemically implausible without invoking some artificial selection process. The silence from mainstream astronomy. What's particularly interesting is how quiet the mainstream astronomical community has been about 3I Atlas. Yes, there are papers, observations, data releases. But compared to the excitement around Umuamua or even Borisov, the public discourse is muted. Part of that might be timing. We're still in the observation phase, and scientists are cautious about making bold claims before the data is fully analyzed. But part of it might also be discomfort. The anomalies are piling up. The anti-tail, the water at 3AU, the nickel without iron, the improbable trajectory, the survival of activity over billions of years. Each one challenges established models. Together, they suggest something fundamentally outside our current framework. Loeb has openly criticized this silence. He's pointed out that many comet specialists are downplaying or ignoring the details that don't fit. They're clinging to the natural comet explanation because the alternative, acknowledging we don't understand this object, opens doors to questions the field isn't ready to confront. What if interstellar space is full of objects that don't behave like our comets? What if our models, built entirely on solar system data, are incomplete? And yes, what if some of these objects aren't natural at all? Those questions are uncomfortable. They threaten careers built on existing paradigms. So the silence continues, and the anomalies are quietly filed away as curiosities. The mothership hypothesis in detail. Loeb's mothership hypothesis isn't just wild speculation. It's a structured argument based on the data. He suggests that 3I Atlas could be a large craft, possibly autonomous, possibly ancient, sent by an extraterrestrial civilization billions of years ago. The cylindrical shape fits. The anti-tail could be a propulsion exhaust or a directed energy system. The nickel ejection could be byproducts of onboard processes, perhaps maintenance systems or energy generation. The water outgassing could be waste venting or coolant systems. The improbable trajectory could be navigation, not chance. The age makes sense. If a civilization wanted to explore the galaxy, they'd send probes designed to last eons. And the timing of arrival near the sun, where gravitational assists are most effective, could indicate intelligent course correction. Loeb goes further. He suggests that if this is a mothership, it might deploy smaller probes, scout craft that separate and remain in the solar system after the mothership leaves. These probes would be too small to detect with current instruments, especially if they're designed for stealth. They could study planets, moons, or simply observe. The mothership, meanwhile, continues on its trajectory, exits the solar system, and moves on to the next star. We'd be left with silent watchers, objects we'd never find unless they wanted to be found. It's a scenario straight out of science fiction, but Loeb argues it's consistent with the data and shouldn't be dismissed without investigation. Why October 29th matters so much. The perihelion date, October 29th, is crucial for multiple reasons. First, it's the point of maximum thermal stress. If 3I Atlas is a comet, this is when it should fragment. The sun's heat will penetrate the nucleus, vaporize subsurface ices, create pressure, and crack the structure apart. We've seen this happen to dozens of comets. It's predictable. If 3I Atlas survives intact, it strongly suggests the object is either far more robust than typical comets, or it's not a comet at all. Second, it's the optimal point for a gravity assist. If this object is under intelligent control, now is the time to adjust trajectory. Use the sun's gravity to accelerate or decelerate, change direction, and set a new course. Any civilization capable of interstellar travel would know this. They'd plan for it. Third, it's when the object is on the opposite side of the sun from Earth. Our view is blocked. Ground-based telescopes can't observe it. Most space-based instruments will have limited angles. If something were going to happen, if probes were going to deploy, if a maneuver were going to occur, this is the window when it could happen undetected. The timing is almost too perfect, and that's what has people like Loeb on edge. We're approaching a critical moment, and we might miss it entirely because of our observational limitations. The velocity anomaly no one is discussing. Here's something that's been buried in the technical data. 3I Atlas entered the solar system at approximately 210,000 kilometers per hour relative to the Sun. That's fast, but within the expected range for interstellar objects. However, as it's moved through the inner solar system, there have been minor velocity variations that don't quite match gravitational predictions. They're small, within the margin of error for most models, so they're not being flagged as significant. But they're there. Tiny accelerations and decelerations that could be explained by outgassing jets. The rocket effect from ejected material providing small thrust changes. That's the standard explanation. But if the outgassing is asymmetric, if it's directional, that implies active venting from specific locations on the object. And if those locations are not random, if there's a pattern, that implies structure. Internal structure directing the outgassing. Which brings us back to the question, natural or artificial? With Umuamua, there was a clear acceleration anomaly that sparked the alien probe debate. With 3I Atlas, the velocity changes are more subtle, but they're present. And combined with everything else, they add another layer to the mystery. If scientists were looking for evidence of active control, this is what the early signs would look like. Small, corrective adjustments. Not dramatic, not obvious, but present in the data if you know where to look. The composition that reveals an alien sun. Let's go deeper into what the 8:1 CO2 to water ratio actually tells us. In our solar system, comets typically have ratios closer to 1:10, or even 1:100, water to CO2. Water ice dominates. But 3I Atlas is reversed. It's 8 times more carbon dioxide than water. That's an extreme composition, and it reveals the environment where this object formed. Specifically, it suggests formation in a region where carbon and oxygen were abundant, but hydrogen was relatively scarce. That points to a star system with different metallicity, different chemical enrichment than our Sun. Possibly an older star from an earlier generation, where the primordial gas had a different composition, or possibly a star that went through a different evolutionary path, enriching its planetary disk with carbon from stellar winds or nearby supernovae. This is exciting because it means 3I Atlas is a direct sample from another star's planetary system. We can analyze it and learn about the conditions around a star we'll never visit. It's a messenger carrying information across light years and billions of years. The carbon-rich signature tells us that planet formation processes vary widely across the galaxy. There's no single template. Every star system is unique, shaped by its local environment, its history, its neighbors. And 3I Atlas is proof of that diversity. It's also a reminder that life, if it exists elsewhere, might emerge in chemical environments radically different from Earth. Carbon-rich worlds with minimal water could still harbor biology, just not biology as we recognize it. The gamma-ray burst connection. There's a speculative but fascinating angle that a few researchers have quietly explored. About 8 billion years ago, when 3I Atlas was likely forming, or had just formed, the galaxy was a more violent place. Gamma-ray bursts were more frequent. Supernovae were exploding in clusters. Star formation was at its peak. If 3I Atlas originated in a region near a gamma-ray burst or a supernova cluster, it could have been exposed to intense radiation and heavy element enrichment. That might explain some of the unusual chemistry. Radiation could have altered surface ices, created exotic compounds, and driven chemical reactions that wouldn't happen in the calmer regions of the modern galaxy. There's also a darker possibility. If 3I Atlas is artificial, and if it was launched billions of years ago, it might have been fleeing something. Gamma-ray bursts sterilize everything within dozens of light years. A civilization facing imminent destruction from a nearby GRB might launch probes, seeds, archives, anything to preserve their existence. 3I Atlas could be a survivor, a relic from a dead civilization, still carrying out its mission long after its creators are gone. That's pure speculation, but it's the kind of scenario that explains why an object this old would still be active, still moving, still functional. It was built to endure. What we learned from Umuamua's mistakes. The first interstellar visitor, Umuamua, taught us a harsh lesson about preparedness. When it was discovered in October 2017, astronomers had only a few weeks to observe it before it sped out of range. By the time the scientific community mobilized, organized observation campaigns, and secured telescope time, it was already too faint and too far away. We got limited spectroscopy, low-resolution images, and fragmentary data. The result was years of speculation and debate with insufficient evidence to reach conclusions. We learned about its unusual acceleration, its elongated shape, its lack of a visible coma. But we never got the detailed measurements we needed. No chemical composition, no surface analysis, no high-resolution imaging, just questions. The astronomy community vowed not to make that mistake again. When Borisov arrived in 2019, the response was faster and more coordinated. Multiple telescopes tracked it, spectroscopy was comprehensive, and we got solid data on its composition and behavior. It was clearly a comet, resembling objects from our own Oort cloud, and the observations confirmed that. With 3I Atlas, the preparation should be even better. We've had months of advance notice. Every major observatory has time allocated. JWST, Hubble, ground-based arrays, radio telescopes, all coordinated. In theory, we should get the most complete dataset ever collected on an interstellar object. But here's the catch. 3I Atlas is moving through a part of its orbit where observational windows are limited. It's approaching the Sun, which means it's increasingly difficult to observe from Earth without the Sun's glare interfering. Space-based observatories have better angles, but even they face constraints. And after perihelion, when it emerges on the far side of the Sun, it will be receding quickly, fading from view. The window for high-quality observation is narrow. If scientists don't capture the critical data in the next few weeks, we'll be back to the Umuamua situation. Endless debates with incomplete evidence. That's what makes this moment so urgent. We have one chance to get this right. The debris field theory. Some researchers are proposing an alternative explanation for the anomalies. What if 3I Atlas isn't a single solid object, but a debris field, a loose collection of fragments held together by weak gravity? That could explain the unusual outgassing patterns. Different fragments, each with different compositions, venting material independently. It could explain the anti-tail if some fragments are ejecting material in unexpected directions. It could even explain the velocity anomalies if the fragments are slowly drifting apart or rearranging themselves. A rubble pile structure, common in asteroids, applied to an ancient interstellar object. This theory has appeal because it stays within natural explanations while accounting for the weird behavior. But it also has problems. Debris fields are unstable over billions of years. The slow drift of fragments would eventually pull them apart, especially after multiple passes through other star systems, gravitational perturbations from giant planets, tidal forces from stellar encounters. For 3I Atlas to still be intact after 7 to 10 billion years suggests either it's more cohesive than a typical rubble pile, or it hasn't experienced the level of disruption we'd expect. Both possibilities raise new questions, and the debris field theory doesn't really address the nickel without iron problem or the industrial compound detection. Those are chemical issues, not structural ones. The detection gap we're not talking about. Here's an uncomfortable truth. Our detection systems are primitive. We found exactly 3 interstellar objects in 8 years of looking. 3. Statistical models suggest that at any given time, there should be thousands of interstellar objects passing through the inner solar system. Thousands. We're seeing a tiny fraction of what's actually out there. Most are too small, too dark, or moving on trajectories we're not monitoring. The Atlas survey, which found 3I Atlas, is one of the best systems we have, and it's still limited to objects above a certain brightness threshold in specific parts of the sky. What this means is that 3I Atlas might not be unique. There could be dozens of similar objects with similar anomalies that have passed through undetected. We might be looking at the tip of the iceberg. If interstellar space is full of ancient, carbon-rich, highly active objects from old star systems, our models of comet behavior and solar system formation are based on a biased sample. We've only studied local objects. We've assumed they're representative. But what if they're not? What if our solar system is the outlier, and the galaxy is full of water-poor, CO2-rich, metal-ejecting objects that don't fit our definitions? That would revolutionize planetary science. And if some of those objects are artificial, if even 1% of interstellar visitors are probes from other civilizations, then the galaxy is far more populated than we've imagined. We're just blind to it. The lingering question of the green glow. That green luminescence keeps coming up in observations. Multiple independent reports, different instruments, consistent description. In comets, green comes from diatomic carbon, C2, which fluoresces under solar UV radiation. But the intensity matters. Normal comets show faint green in their comas. 3I Atlas is reportedly brighter, more saturated. That could just be higher carbon content, consistent with the CO2-rich composition. But there's another possibility that's been whispered in speculative circles. What if the green isn't from carbon at all? What if it's from something else, something artificial? Certain industrial processes produce green emissions. Copper compounds, for example, barium, thallium, various phosphorescent materials. If there's any kind of artificial system on board, any electronics or chemical processes involving these elements, they could produce visible light in the green spectrum. It's a stretch, absolutely. There's no evidence for this beyond the color itself. But it's the kind of detail that in hindsight might matter. If 3I Atlas turns out to be artificial, people will go back and re-examine every observation, every spectral line, looking for clues we missed. The green glow will be one of them. How close will it actually get? Let's clarify the distances, because there's been some confusion in public reporting. 3I Atlas will reach perihelion, its closest approach to the Sun, on October 29th at about 0.89 astronomical units. That's closer than Earth, roughly the same distance as Venus orbits. It's close, but not dangerously so. The Sun won't gravitationally capture it. Its velocity is too high. After perihelion, it will swing past and head back out toward interstellar space. The closest approach to Earth happens later, on December 19th, at approximately 260 million kilometers, about 1.74 AU. That's almost twice the distance from Earth to the Sun. Still far, no risk of collision, but close enough that powerful telescopes should get decent resolution if the object hasn't fragmented by then. One interesting detail, at its closest point to the Sun, 3I Atlas will be moving at its maximum velocity relative to the Sun, over 300,000 kilometers per hour due to gravitational acceleration. If it were under power, if engines were firing, the velocity change would be masked by the natural acceleration from gravity. That's why perihelion is such a clever point for a maneuver. Any artificial thrust would be hidden in the noise. Observers would see velocity changes and attribute them to gravity. Unless the thrust was enormous, creating acceleration beyond what gravity alone could explain, it would be invisible. And if the object is designed for stealth, the thrust would be precisely calibrated to stay within expected ranges. We'd never know. The JUICE probe's unique opportunity. The European Space Agency's JUICE spacecraft, currently en route to Jupiter, will have an unusual viewing angle of 3I Atlas in November and December. Because JUICE is not orbiting Earth, it's on an independent trajectory. It will see 3I Atlas from a perspective that ground-based and Earth orbit telescopes can't match. That's valuable. Different angles reveal different details. If 3I Atlas has asymmetric features, jets coming from specific locations, or structural anomalies, JUICE might catch what others miss. It's not a dedicated observation. JUICE's instruments are optimized for Jupiter and its moons, but the ESA has confirmed they'll turn the cameras toward 3I Atlas when the geometry is favorable. This is one of those fortunate accidents. JUICE wasn't designed to study interstellar objects, but its position in space makes it a useful observer. The data it collects, even if limited, will complement the Earth-based observations. Multiple viewpoints are critical in astronomy. They allow for triangulation, depth perception, and confirmation of features that might be artifacts in single telescope images. If JUICE sees the same anomalies everyone else is seeing, it strengthens the case that those anomalies are real. And if JUICE sees something different, something hidden from our viewpoint, that could be the revelation that changes everything. Why the 0.2% probability trajectory matters more than you think. Let's break down what that statistic actually means. When astronomers calculate the probability of an interstellar object entering the solar system on a specific trajectory, they're considering the entire sphere of possible entry angles, velocities, and orbital inclinations. The solar system is like a tiny target in the vastness of space. An object coming from any random direction in the galaxy has an effectively infinite number of possible paths. The fact that 3I Atlas entered on a retrograde orbit, moving opposite to the planets, is already unusual. About a 50-50 split. But the orbital inclination, only 5 degrees off the ecliptic plane, is where it gets statistically weird. Most interstellar objects should enter from high inclinations, steep angles, because there's more volume of space above and below the solar system plane than within it. It's a geometric fact. Objects arriving nearly in the plane of the solar system are rare. The 0.2% probability reflects this. But here's why it matters. If 3I Atlas were navigating, if it wanted to survey the planets, it would choose a low inclination orbit. That gives maximum exposure to the plane where all the interesting objects are. The rocky planets, the asteroid belt, the gas giants. A high inclination flyby would miss most of the solar system's features, zipping over or under everything. A low inclination, retrograde orbit allows a slow pass through the system, time to observe, time to collect data. It's the trajectory you'd choose if you were exploring. The fact that nature randomly selected this trajectory is possible, but unlikely. The fact that an intelligent system chose it is consistent with mission design. The technological signatures we could be missing. If 3I Atlas is artificial, what would the signatures look like? Probably not radio transmissions. lasers, or obvious electromagnetic emissions. A probe designed for long-duration stealth would minimize detectable output. But there are subtler signs. Spectral absorption lines that don't match known molecules. Thermal emissions inconsistent with solar heating alone. Polarization patterns in reflected light suggesting manufactured surfaces. Variations in brightness that aren't explained by rotation or outgassing. These are the kinds of anomalies that require careful analysis and comparison with models. They don't jump out of the data. You have to look for them. Some researchers are running machine learning algorithms on the observational data, training neural networks to recognize patterns that human analysts might miss. If there's a structure, a regularity in the emissions or the light curves, AI might find it. But this work is slow and underfunded. Most of the effort is going into conventional analysis, fitting 3i Atlas into existing Comet models. The unconventional searches, the SETI-style investigations, are happening on the margins, often by scientists working in their spare time. That's a problem. If we're going to seriously consider the artificial hypothesis, we need dedicated resources, dedicated teams, and dedicated observation time. We're not there yet. The astronomical establishment is still treating 3i Atlas as an exotic comet, not a potential contact event. The fragmentation question and what it reveals. Whether 3i Atlas fragments at perihelion is the single most diagnostic observation we can make. Comets fragment because they're fragile. They're loose aggregates of ice and dust, held together by weak cohesion and microgravity. When they get close to the sun, thermal stress creates internal pressure, and they crack apart. We've watched it happen dozens of times. If 3i Atlas fragments, it confirms it's a comet, regardless of the chemical oddities. The structure would be natural. The anomalies would be explained as rare but possible variations in comet composition and behavior. But if it doesn't fragment, if it survives perihelion intact and continues on its trajectory without breaking up, that's a problem for the comet hypothesis. Objects that survive, that level of thermal stress, are either incredibly dense and cohesive, like solid rock or metal, or they're structurally engineered. Natural comets aren't dense enough or strong enough to hold together under those conditions. Umuamua didn't get close enough to the sun for us to test this, and it didn't have a visible coma, so its classification remains ambiguous. Borisov stayed farther out and behaved like a normal comet. 3i Atlas is going in close, into the danger zone. We'll see what it's made of. Literally. And that will tell us what it is. The three-body problem and gravitational choreography. There's a subtlety in 3i Atlas's trajectory that orbital mechanics specialists have noted. As it moves through the inner solar system, it's not just interacting with the sun. It's passing through the gravitational influence zones of multiple planets: Venus, Earth, Mars, Jupiter. Each one exerts a pull, however slight. For a random interstellar object, these interactions should create small, unpredictable perturbations in the orbit. Chaotic influences that make long-term trajectory prediction difficult. But 3i Atlas's path has been remarkably stable. The perturbations are there, but they're within predictable bounds, almost as if the trajectory was calculated to minimize disruptive gravitational encounters. This could be coincidence. The object might have just happened to enter at an angle and velocity that naturally avoids strong planetary interactions. But orbital mechanics is complex. The probability space is vast. Finding a trajectory that threads through the gravitational maze of the inner solar system without significant deflection is like throwing a ball through a spinning fan and having it pass cleanly between the blades. Possible, but impressive. If 3i Atlas were navigated, this is exactly what mission planners would aim for. A clean pass through the system, minimal deflection, maintain the intended course. The math works either way, nature or intelligence. But one requires luck, and the other requires calculation. What the spectral lines are hiding. Spectroscopy is powerful, but it has limitations. We see absorption and emission lines corresponding to known molecules: water, carbon dioxide, carbon monoxide, cyanide, nickel compounds. But spectral analysis assumes we know what we're looking for. If there's something on or in 3i Atlas that we don't have in our spectral databases, we won't recognize it. The instruments will record the lines, but the analysis software will flag them as noise or unknown contaminants. It takes a human expert reviewing the raw data to notice something genuinely new. There are rumors, unconfirmed and circulating in online astronomy forums, that some spectroscopists have flagged unusual lines in the 3i Atlas data, lines that don't match any cataloged molecule. The mainstream interpretation is that these are artifacts, calibration errors, or known molecules in unusual states. But a few researchers are quietly investigating the possibility of unknown chemistry. If 3i Atlas formed in a drastically different environment, it might contain molecules that don't exist anywhere in our solar system. Exotic ices, unusual carbon chains, metal organic compounds we've never synthesized. Discovering a new molecule would be a major scientific breakthrough. Discovering several would suggest we're looking at chemistry from an entirely different cosmic ecosystem, the speed at which it's shedding mass. 40 kilograms of water per second is just one component of the outgassing. There's also CO2, CO, dust, and those nickel compounds. If you sum up all the material 3i Atlas is ejecting, the total mass loss is somewhere in the range of 50 to 60 kilograms per second. That's over 5,000 kilograms per day, nearly 150,000 kilograms per month. It's been active since at least August, when the anti-tail was first observed. That's already over 300,000 kilograms lost, and it's accelerating as it approaches perihelion. By the time it leaves the inner solar system, it could shed several million kilograms. Here's the question: how much mass does it have to begin with? If the nucleus is 2 to 6 kilometers across, and we assume a comet-like density around 0.6 grams per cubic centimeter, the total mass would be somewhere between 2 trillion and 70 trillion kilograms, depending on size. Losing a few million kilograms is negligible for the larger estimates, but if it's on the smaller end, 2 kilometers across, and the activity continues at this rate, it could lose a measurable fraction of its total mass. That might change its appearance, its brightness, even its orbit slightly. Observers are watching for signs of shrinkage, dimming, or structural changes. If the object is artificial, and the outgassing is vented waste or propellant, the mass loss budget would be pre-calculated. It wouldn't shed more than it can afford to lose. That's another potential test. Does the outgassing stop abruptly at some point, suggesting reserves are managed? Or does it continue uncontrolled, like a natural comet? The magnetometer readings we're not getting. One of the most frustrating gaps in our observation capability is magnetic field measurement. To properly characterize 3i Atlas, we'd need a spacecraft with a magnetometer to fly close and measure any magnetic fields. Comets don't typically have strong intrinsic magnetic fields. They're not large enough or dense enough to have active dynamos. But metal-rich objects, or objects with electrical systems, would generate fields. If 3i Atlas has a metallic core, or if it's artificial with active electronics, there would be a detectable magnetic signature. We're not going to get that data. No mission was prepared in time. We're limited to remote sensing, light, spectra, radio, no in situ measurements. It's like trying to diagnose a machine by looking at it from across the room. You can see what it's doing, but you can't understand how it works. This is one of the arguments for rapid response space missions. When an interstellar object is detected, we should have a probe ready to launch on short notice, intercept the object, and collect data up close. The technology exists. Fast, small probes with ion drives could reach these objects if launched within weeks of detection. But the funding and political will aren't there. Space agencies move slowly. By the time a mission is approved, designed, and built, the object is long gone. We've missed Umuamua, Borisov, and now we're missing Three-Eye Atlas. The fourth interstellar object might be the charm if we learn from these missed opportunities. The silence from SETI. The search for extraterrestrial intelligence has been monitoring Three-Eye Atlas since its discovery. SETI's radio telescopes, including the Allen Telescope Array and facilities associated with Breakthrough Listen, have scanned the object across multiple frequencies. They're looking for any coherent signals, repeated patterns, or narrow band emissions that would indicate artificial origin. So far, publicly at least, they've reported nothing. No radio transmissions, no laser pulses, no detectable communication. That's either reassuring or expected, depending on your perspective. If Three-Eye Atlas is a probe, it might not be transmitting. Why would it? Its mission could be purely observational, or it could transmit on frequencies or with modulation schemes we're not monitoring, or it could use directional beams aimed elsewhere, not at us. The absence of detectable signals doesn't prove it's natural. It just means we haven't found evidence of artificiality through electromagnetic emissions. SETI's null result is data, but it's not conclusive. Loeb has pointed this out repeatedly. The lack of a signal is not the same as proof of natural origin. It simply narrows the possibilities. If Three-Eye Atlas is artificial, it's not broadcasting. That's all we can say. The historical precedents that should worry us. This isn't the first time humanity has encountered something anomalous in the sky and defaulted to natural explanations. For decades, ball lightning was dismissed as optical illusions or misidentified phenomena because it didn't fit the physics models. It took laboratory recreation and high-speed cameras to confirm it was real. Fast radio bursts were initially thought to be equipment malfunctions or Earth-based interference. Now we know they're real, extragalactic events, though we still don't fully understand them. The point is, science has a conservatism bias. When something doesn't fit the models, the first instinct is to dismiss it or reinterpret it until it does fit. That's usually correct. Most anomalies turn out to be errors, misunderstandings, or natural phenomena we haven't encountered before. But occasionally, the anomaly is genuine. It's something new, something that requires revising the models. And the longer we cling to the old explanations, the longer we delay understanding. Three-Eye Atlas might be a comet. The safest bet is that it's a comet. But the accumulation of anomalies, the pattern of behaviors that don't quite fit, should at least make us consider that we're looking at something outside our current categories. Not jumping to conclusions, but remaining open to evidence. That's the scientific ideal. In practice, careers, funding, and reputations are tied to existing frameworks, and that creates resistance to paradigm shifts. It's not malice. It's human nature, but it can blind us to what's right in front of us. Why Loeb is willing to stake his reputation. Avi Loeb is a full professor at Harvard, chair of the astronomy department, a respected researcher with hundreds of publications. He's not a fringe figure, he's establishment. Yet he's been vocal about the possibility of extraterrestrial artifacts in our solar system, first with Umuamua, now with Three-Eye Atlas. This has cost him. Colleagues have criticized him, some publicly. He's been accused of sensationalism, of abandoning scientific rigor for media attention. Yet he persists. Why? Loeb's argument is philosophical. He believes science should follow the evidence wherever it leads, even if the destination is uncomfortable. If the data suggests artificial origin is possible, we should investigate that hypothesis rigorously, not dismiss it out of hand. He's also argued that the stigma around searching for extraterrestrial technology is unscientific. We accept the possibility of microbial life on Mars or Europa. We search for biosignatures in exoplanet atmospheres. But when it comes to technosignatures, advanced civilizations, there's a reluctance to engage seriously. It's seen as fringe, as ufology, not proper science. Loeb is pushing back against that stigma. He's willing to take the professional risk because he believes the question is important and the evidence warrants attention. Whether you agree with his conclusions or not, his willingness to openly discuss these possibilities is valuable. It creates space for other scientists to ask unconventional questions without fear of career suicide. It shifts the Overton window of acceptable scientific discourse. And if he's wrong, if 3I Atlas turns out to be a normal comet, he'll have contributed to the dialogue and accepted the criticism. But if he's right, if any of these interstellar objects turn out to be artificial, his early advocacy will be vindicated. He's playing a long game, betting that history will judge him more kindly than his current peers. The other comets that didn't behave. 3I Atlas isn't the only comet to show anomalous behavior. There's a long history of comets doing unexpected things. Comet Schwarzmann-Wachmann. 1. Orbits between Jupiter and Saturn and undergoes sudden outbursts with no apparent cause. Comet 17P Holmes brightened by a factor of 1,000,000 in 2007, turning from an invisible speck into a naked eye object overnight. Comet Borisov had that unusually high CO content. Even some Oort cloud comets show composition variations that don't fit standard models. The difference is that those are solar system objects. We can attribute their oddities to local formation conditions, collisional history, or evolutionary changes over time. 3I Atlas doesn't have that luxury. It's from outside. We can't invoke solar system processes to explain it. Whatever made it weird happened in another star system, under conditions we can only guess at. But here's the interesting part. If we're seeing anomalies in solar system comets, objects we've studied extensively, how much weirder could interstellar comets be? We're working from a sample size of 3 interstellar objects. That's not enough to establish norms. We don't know what's typical and what's extraordinary. 3I Atlas might represent the average interstellar comet, and our solar system comets might be the outliers. We won't know until we detect dozens, hundreds of interstellar visitors and can perform statistical analysis. Until then, every interstellar object is potentially a unique puzzle, and we have to resist the urge to force it into boxes designed for local objects. What happens if it does turn out to be artificial? Let's entertain the scenario. Suppose observations over the next few weeks provide compelling evidence that 3I Atlas is not natural. Maybe it doesn't fragment. Maybe the spectral lines reveal manufactured materials. Maybe the trajectory changes in ways that can't be explained by outgassing. Maybe the juice probe images show geometric structures. At what point does the scientific consensus shift? And what happens next? The immediate impact would be on the astronomical community. Papers would be rushed to publication. Observation time would be reallocated. Funding would pour in. Every telescope on Earth and in space would track 3I Atlas until it's too faint to observe. International collaborations would form. Governments would get involved because the discovery of extraterrestrial technology has security and policy implications. The media would explode. It would dominate headlines for months. Forget politics, economics, entertainment. This would be the only story. Humanity's first confirmed encounter with evidence of another civilization. The philosophical and cultural ramifications would be profound. But here's the unsettling part. We wouldn't be able to communicate with it. If it's a probe, and it's not transmitting, we can't talk to it. We can observe it, analyze it, speculate about it, but we can't interact. It would be like archaeologists discovering an ancient artifact with no idea who made it, when, or why. We'd study it as it passes through and leaves. And then we'd be left with the knowledge that we're not alone, that intelligence exists or existed elsewhere, that they achieved interstellar travel, and that they've been to our solar system. But we wouldn't have answers, just more questions. Who sent it? When? Why? Are they still out there? Are there more probes? What do they want? We'd be haunted by those questions for generations. The countdown to October 29th. We're days away from the critical moment. As this script is being prepared, 3i Atlas is closing in on the sun. Telescopes are locked on. Data is streaming in. Somewhere, in observatories around the world and in space, astronomers are watching screens, running analysis, comparing models. They're waiting to see what happens. Will it fragment? Will it survive? Will it change trajectory? Will there be any sign, any hint that this is more than just a comet? The smart money is on natural origin. Comets do weird things sometimes, and 3i Atlas, however strange, will probably fit within the broad spectrum of comet behavior once all the data is in. The anomalies will be explained. The anti-tail will turn out to be an optical illusion or unusual dust dynamics. The nickel without iron will be a detection error or a rare mineralogy. The water at 3AU will be powered by something mundane, volatiles we didn't account for. The trajectory will be chalked up to luck, and life will go on with one more interstellar comet cataloged and filed away. But there's a non-zero chance, small but real, that we're about to witness something historic. That 3i Atlas will do something, show something, reveal something that forces us to reconsider everything. And if that happens, October 29th, 2025, will be remembered as the day we confirmed we're not alone. The day a visitor from the stars, whether a comet or a craft, passed through our solar system and left us with undeniable evidence that the universe is far more interesting and far more populated than we dared to believe. The public reaction that's already building. Look at social media, astronomy forums, YouTube comment sections. There's a growing awareness of 3i Atlas among space enthusiasts and the general public. People are sharing the latest images, speculating about its nature, posting theories ranging from scientifically grounded to wildly imaginative. The hashtags are trending periodically. Some are treating it as pure entertainment, the latest cosmic mystery to follow. Others are genuinely concerned, asking if there's any danger, if governments are hiding information, if this could be first contact. The response is diverse, but the engagement is real. People care about this object in ways they didn't care about Borisov. Part of that is the timing. We're in a cultural moment where UAP disclosure, Pentagon reports, and congressional hearings have made the topic of potential non-human intelligence more mainstream. The stigma is lifting. People are more willing to entertain the possibility that we might not be alone. 3i Atlas arrives in this context, and it fits the narrative. An anomalous object from outside our solar system, exhibiting behaviors that challenge conventional explanations. Whether it's a comet or not, it's captured the public imagination. And that public interest is putting pressure on scientists and institutions to take the anomalies seriously, to investigate thoroughly, and to communicate findings transparently. What the amateurs are finding. Professional astronomers aren't the only ones watching. Amateur astronomers with backyard telescopes, astrophotographers with high-end cameras, citizen scientists analyzing publicly available data. They're all contributing. And some of them are finding interesting things. There are reports of brightness fluctuations that don't match the expected rotation period. Claims of asymmetric coma structure, with more activity on one side than the other. Images showing color variations across the object's surface. None of this has been peer-reviewed or confirmed by professional analysis, so it exists in a gray zone of uncertain reliability. But historically, amateurs have made significant contributions to astronomy. Comets are often discovered by amateurs. Supernovae, variable stars, asteroids. The crowdsourced observation of 3i Atlas is generating a wealth of data, some of which might contain clues the professionals miss. The challenge is separating signal from noise. Amateurs work with different equipment, different calibration standards, different levels of expertise. Artifacts, processing errors, and wishful thinking can create apparent anomalies that aren't real, but dismissing all amateur contributions would be a mistake. The distributed observation network, thousands of eyes on the sky, increases the chances that something unusual will be caught. If 3-Eye Atlas does something brief, something transient, a professional observatory might miss it due to weather, scheduling, or bad timing, but an amateur somewhere might catch it. That's the value of the crowd, redundancy, and coverage. The parallel to Umuamua's acceleration. Let's revisit the Umuamua situation, because it's directly relevant. When Umuamua's trajectory was analyzed in detail, astronomers noticed it was accelerating slightly as it left the solar system. Not much, but measurable. That acceleration couldn't be explained by gravity alone. The most common explanation was outgassing, the rocket effect. As material vents off a comet, it provides a tiny thrust. That's normal. The problem was that Umuamua showed no visible coma, no tail, no signs of outgassing. So where was the thrust coming from? Various theories emerged. Maybe it was outgassing pure hydrogen or some other invisible gas. Maybe it was a chunk of solid hydrogen ice, exotic but possible. Maybe it was a light sail, a thin artificial structure pushed by solar radiation, the explanation Loeb favored. Maybe it was a fractal iceberg with high surface area. Every explanation required invoking something unusual, something we hadn't seen before. The debate continues to this day. Umuamua left us with an unsolved mystery. Now, with 3-Eye Atlas, we're seeing velocity variations again. And this time, there's visible outgassing, so the rocket effect is a more plausible explanation. But if the velocity changes don't correlate with the observed outgassing, if the thrust is too strong or in the wrong direction, we're back to the Umuamua problem, unexplained acceleration. And that's when things get really interesting. The isotope ratios we desperately need. One of the most diagnostic measurements we could make on 3-Eye Atlas is isotope analysis. Isotopes are versions of the same element with different numbers of neutrons. The ratios of isotopes, like carbon-12 to carbon-13, or oxygen-16 to oxygen-18, vary depending on where and how the material formed. In our solar system, we have baseline isotope ratios that are fairly consistent, set by the composition of the molecular cloud that collapsed to form the sun and planets. But other star systems, formed from different clouds with different histories, would have different ratios. If we could measure the isotope ratios in 3-Eye Atlas's outgassing, we could confirm beyond doubt that it's truly interstellar and learn about the chemical environment of its home system. The problem is that isotope measurements require high-resolution spectroscopy, the kind you get with large, specialized instruments. And you need a lot of signal, a bright target. 3-Eye Atlas is faint and distant for most of the observation period. By the time it's bright enough for detailed spectroscopy, it's close to the sun, which makes observations difficult. There's a narrow window, and it's not clear if we'll capture the data. If we do, and the isotope ratios are wildly different from solar system values, that's strong evidence for interstellar origin and exotic formation conditions. If they're similar, it raises questions about convergence in stellar chemistry or contamination from solar-wind interactions. Either way, it's valuable information, but we might not get it. And that would be another missed opportunity in a long list of missed opportunities with interstellar objects. Why the cylindrical shape is so provocative. Shapes matter in astronomy. Most comets and asteroids are irregular, lumpy, potato-shaped. That's the natural result of accretion and collisions. Material sticks together randomly. Gravity pulls it into a rough sphere if it's large enough, but for smaller objects, you get irregular shapes. Spheres and ellipsoids are common. Cylinders are not. A cylinder requires either a very specific formation process or deliberate construction. In nature, cylindrical shapes can arise from certain crystallization processes, or from rotational dynamics that stretch an object along one axis. But in comets and asteroids, true cylinders are virtually unknown. Umuamua was described as elongated, with an aspect ratio somewhere between 5:1 and 10.1, possibly cigar-shaped or pancake-shaped depending on interpretation. That alone sparked debate. 3I Atlas is now being described as cylindrical by some observers. If that's accurate, it's unusual. It suggests structure, alignment, uniformity. Those are traits we associate with artificial objects. Rockets are cylindrical. Spacecraft are often cylindrical. It's an efficient shape for certain engineering purposes, maximizing internal volume while minimizing surface area. If 3I Atlas truly has a cylindrical form, and that's confirmed by multiple independent observations from different angles, it would be one of the strongest pieces of evidence for artificiality. But shape determination for distant, faint objects is notoriously difficult. Rotation, lighting, perspective all influence what we see. We need better images, higher resolution, ideally from JUICE or other spacecraft, to settle the shape question definitively. The nuclear option, sending a mission. There's been informal talk in space agency circles about sending a rapid response mission to 3I Atlas, not to intercept it while it's still in the inner solar system. That window is too narrow, but to launch a fast probe that catches up with it after it leaves, matches velocity, and conducts close-range observations. The technology exists. High-speed ion drives, flyby probes, even sample return missions are technically feasible. The engineering challenges are significant, but not insurmountable. The real barriers are cost, time, and political will. Such a mission would cost billions. It would require international cooperation, rapid development cycles, and acceptance of high risk. There's no guarantee the probe would function correctly after a multi-year journey at high speed. There's no guarantee 3I Atlas would still be intact or active by the time the probe arrives. But the scientific payoff would be unprecedented. Close-range imaging, spectroscopy, magnetic field measurements, maybe even physical samples. We'd answer the question of what 3I Atlas is definitively, and we'd establish a template for future missions to interstellar objects. The capability to intercept and study these visitors up close would revolutionize our understanding of the galaxy. But will it happen? Probably not for 3I Atlas. The decision-making process is too slow. By the time funding is approved and hardware is built, the object will be decades away, too far and too faint to catch. But maybe for the fourth interstellar object, if we detect it early enough, there will be political and public will to act. 3I Atlas might be the catalyst that makes that happen. The philosophical weight of confirmation. Imagine for a moment that the evidence becomes overwhelming. That multiple independent lines of data converge on the conclusion that 3I Atlas is artificial. What does that do to humanity's self-conception? We've spent millennia assuming we're alone, or at least that we're the only intelligence in our immediate cosmic neighborhood. The Copernican principle, the idea that we're not special, that Earth is just another planet around just another star, has been philosophically accepted. But emotionally, culturally, we've still held on to a kind of cosmic exceptionalism. We're the ones who built civilizations, who developed science, who reached for the stars. Confirmation of extraterrestrial technology shatters that. Not only are we not alone, but someone else got there first. Someone else achieved interstellar travel, possibly billions of years ago, while our ancestors were still single-celled organisms floating in ancient oceans. We're the newcomers, the latecomers, and we're being observed, or at least our solar system is. That's humbling in a way that's hard to articulate. It recontextualizes all of human history. Our wars, our achievements, our struggles, they're all local events on a small world, playing out under the watch of a wider cosmos that we're only beginning to understand. Some people would find that perspective liberating. Others would find it terrifying. But no one would be unaffected. The confirmation of extraterrestrial intelligence would be the most significant event in human history. Period. Everything after would be divided into before and after that revelation. The waiting game and what to watch for. So what should we be looking for in the coming days and weeks? First, fragmentation. If 3i Atlas breaks apart near perihelion, that's a strong indicator it's a natural comet. Look for reports of multiple fragments, brightening due to increased surface area, and eventual fading as the pieces disperse. Second, trajectory changes. If the object's path deviates from gravitational predictions in ways that can't be explained by symmetric outgassing, that's a red flag. Third, spectral anomalies. If new, unidentified lines appear in the spectrum, especially near perihelion when the object is most active, that could indicate unusual chemistry or materials. Fourth, structural features. If JUICE or ground-based telescopes with adaptive optics resolve any geometric shapes, patterns, or surface features inconsistent with natural comets, that's significant. Fifth, brightness variations. If the brightness changes in ways that don't correlate with distance from the sun or expected rotation, it might indicate active processes or internal changes. Sixth, and this is subtle, watch for institutional reactions. If there's a sudden increase in classified observation time, if military or intelligence telescopes start tracking the object, if there are unexplained communication blackouts among research teams, those could be indirect signals that something unexpected has been discovered. The absence of information can be informative. Finally, listen to the scientists who are actually analyzing the data. Not the media summaries, not the press releases, but the researchers themselves. When they start using careful, hedged language, when they avoid committing to conclusions, when they say things like further investigation is needed, or the results are inconsistent with standard models, that's when you know something genuinely weird is happening. The legacy of 3i Atlas regardless of outcome. Whether 3i Atlas turns out to be a comet or something more, it's already a milestone. It's the third confirmed interstellar object, and the first one we've had months to study in advance. The data collected will inform models of interstellar chemistry, comet behavior, and planetary system diversity for years. It's proven that our detection systems are improving. We're finding these objects faster and tracking them more effectively. It's demonstrated that public interest in astronomy remains strong, that people care about cosmic mysteries and want to be part of the discovery process. And it's forced the scientific community to grapple with uncomfortable questions about how we handle anomalies, how we balance skepticism with open-mindedness, and how we prepare for the possibility of contact with extraterrestrial intelligence. If it's a comet, we'll learn from it and move on. But the questions it raised won't disappear. The next interstellar object will be scrutinized, just as intensely, maybe more so. We're building a framework, a methodology, for dealing with these visitors. And eventually, one of them will be undeniably different. Maybe not 3i Atlas. Maybe not the fourth or fifth object. But eventually, statistically, we'll encounter something that can't be explained naturally. And when that happens, we'll be slightly more prepared because of 3i Atlas. Because of the debates it sparked, the observations it demanded, and the boundaries it pushed. That's its legacy, no matter what it is. It made us think harder, look closer, and question more. And that's exactly what science should do. The final countdown. We're in the last stretch now. 3i Atlas is accelerating toward the sun, its activity increasing, its mysteries deepening. Observatories around the world are locked on target. Data is accumulating. Researchers are running simulations, comparing models, preparing papers. In a matter of days, we'll have answers to at least some of the questions. Will it fragment or survive? Will it change course or follow predictions? Will it reveal its nature or remain enigmatic? the anticipation is building, not just in the scientific community, but among anyone paying attention to this cosmic drama. And here's the thing. Whatever happens, this is a moment worth witnessing. We're living through the early stages of humanity becoming a spacefaring species aware of a larger cosmic community. Whether that community consists only of lifeless rocks and ice balls, or whether it includes artifacts of intelligence, we're learning. We're expanding our perspective. We're confronting the reality that the universe is vast, old, and full of things we don't yet understand. 3i Atlas is one chapter in that story, a compelling, mysterious, potentially paradigm-shifting chapter, and we get to watch it unfold in real time. So pay attention, follow the news, look at the images, read the papers, join the conversation. Because moments like this are rare. The arrival of a visitor from another star system, carrying information and perhaps secrets from across the galaxy, is not something that happens every day. It's happening now. And whatever the final verdict on 3i Atlas, whether comet or craft, natural wonder or artificial marvel, it's a reminder that we live in an extraordinary universe. And that the most interesting discoveries are often the ones we didn't expect, found in places we weren't looking, challenging us to think bigger and reach further than we ever imagined.